Everyone, welcome to this lecture on spherical polar coordinates. Actually, we'll be moving further now because actually last time we talked about cylindrical and spherical polar coordinates. So this will primarily concern ourselves with more examples in which we talk about applications of these coordinate systems. So I've realized in the previous video, I think I've made a small mistake. So I would like to just for practice purposes, I would just like to derive acceleration in polar coordinates, right? And we will see a direct application on that. Okay, so we'll see a direct application on that, and that is we'll concern ourselves with central forces, right? We will concern ourselves with central forces. Okay, so this is a direct application of that. So first of all, when we talked about polar coordinates, just a revision, we talked about how a particle is at moving in a circle, right? And we defined an infinitesimal position vector. dr is dr r cap plus r d theta theta cap, because the object has a radial component and a transverse component. So this is the radial, so this is the radial component and this is the transverse component. So then we went along and defined velocity, that is basically the time derivative, right? And the radius is again, this is a constant, so we take it out and then we just differentiate this, right? Okay, so this is the your velocity is basically r dot r cap plus r theta dot theta cap. Okay, so this is your velocity in polar coordinates. This is your velocity in polar coordinates. So further we can define our acceleration, right? So again we do it. So I will be doing a derivation again. So you can skip to the further parts of the video if you don't want to see this derivation, but I think it is good to do this derivation because even I've made this mistake. So I'm just using product rule. Okay, so we have these quantities, right? So we have a time derivative in the unit vector, as you can see here. So going back, so you can go back to the previous video and recall that we had defined r cap as cos theta I cap plus sin theta j cap, and since r cap and theta cap are orthogonal to each other, we will say that theta cap is sin theta I cap plus cos theta j cap, just the derivative. You can see you can dot the two vectors. You can see that this is 0, so they are orthogonal. So they are orthogonal to each other. Anyways, so let's proceed. So and yes, so once you derivate them, right, r dot cap is basically r cap dot is basically minus sin theta I cap plus cos theta j cap theta dot, because of chain rule, and this will be minus cos theta I cap plus sorry, minus sine theta j cap theta dot. So I can further represent it as theta cap theta dot minus r cap theta dot. So you can verify these once again. Okay, and the acceleration becomes r dot r cap plus theta dot r dot theta cap. So I'm just substituting this into this. Okay, and I'm substituting this into this. R dot theta dot theta cap plus r theta dot so your final thing is going to be just pairing up the terms, right? So r dot minus r theta dot squared r cap plus 2 r dot theta dot plus r double theta dot theta cap, and this is your acceleration in planar coordinates. This is your acceleration in planar coordinates. So this derivation has been asked in my experience many times. So it is, I mean, it is, once you keep doing it, you will eventually memorize it. But it is always good to keep this derivation in hand. Okay. So, okay. So the direct application of this, anyways, in the last lectures also I was telling, is your central forces. So by central forces, I mean the motion of celestial bodies. So central forces generally have a few properties, right? So that means forces which act along the line joining two bodies and whose magnitudes depends on the distance between two bodies. So your gravitational force is central force, right? So concerning ourselves with central forces, right, you have the sun here and then you have earth here at one of the, so sun is at one of the foci, right, in an ellipse. It's not a perfect ellipse, and you have earth in another one, and basically central forces are basically forces acting along the line joining two bodies, and they are also their magnitude depends upon distance between two bodies, right? So that's why, you know, when if you, so for example, if I draw the axis here, right, so this is the origin, all right. So I have a position vector that goes from sun to earth here, okay, and I have so basically this distance, right, this distance is going to determine the force that is acting between the two bodies. Okay, I mean, I'm taking sun as origin here. I can also take another origin. I'll draw it in red right here. Okay, so I can call this new point O. Okay, and I can draw a position vector to the sun, and I can draw another position vector to the earth, and the distance between the earth and sun, I can call it R. So this is R1. Distance from origin to sun is R1. Distance from origin to earth is R2, and I can call the distance R1 minus R2. Right? R2 minus R1. Whatever. So it all depends on convention. Okay. So if I take this is the vector here. So this is r2 minus r1. So in vectorial form, we know that distance between Earth and Sun is r2 vector minus r1. Okay, so magnitude will be just that, and you can also define a unit vector. I'm not putting the arrows anymore. That's this. So your force is going to be a function of r with this vector pointed radially outward, and that becomes an important point in mostly in central force problems, right? So this will be and I'm putting a minus sign because it is an attractive force, and m1 and m2 is mass of Sun and Earth, but usually mass of Earth is, since it's very less, you can also, the mass of Sun only takes over, but for simplicity, so it depends on both the masses, right? So vectorially it is represented like this. Okay, vectorially it is represented like this, and in a more important thing, your gravitational force is a central force. So we have discovered our first central force, and there are many other examples of other such central forces, but your gravitational force is a central force. Okay, so its magnitude depends upon the distance between two bodies and acts along the line joining two bodies. Electrostatic force is another example. So next we go to conservative forces. Your gravitational force and your electrostatic force is a conservative force. So what does that mean? So I'll just add it here. It is also a conservative force. What does that mean? Conservative force? The work done to move the body from one point to another is zero. That is all. And you can also prove this. So if you have studied Stokes' theorem, this might makes more sense to you. But so basically, Stokes' theorem is your gradient, the curl in a closed loop is equal to the line integral of the force. So conservative forces, so the work done to move a body in a closed loop is zero, right? So this becomes zero. So actually this part of the proof becomes more important in the next the thing that I'm going to talk about next. So maybe let's not do it yet. But yeah, anyways, so regardless, if you, so for example, if I take a box and then I move a distance, I'm technically doing no work because gravity is a conservative force. So you are doing no work, but in physics terms. But obviously you are expending some amount of your energy to carry the box from one point to another. So the one of the most important points here is that, right, conservative forces can be expressed as a gradient of a scalar potential as well. Okay, conservative forces can be expressed as a gradient of scalar potential. So that means I can express my force, this force, right, that we have defined here, as a gradient of some gradient of a scalar potential. And this negative sign becomes important because it is uh, technically for so I mean, you can say it's notation, but more than that, I would say, for example, you have a ball, right? You have a ball and you're moving it against gravity, right? So your potential energy is going to be mgh. So uh, your force obviously is going to be mg, but your force is acting against gravity. It is always going to be acting against gravity, and it's also attractive, because obviously once you drop the ball, it's going to come down, right? So this negative sign comes from the fact that that is, the forces act opposite to the direction of increase in potential energy. So as you keep increasing the potential energy, as you keep bringing the ball up, right, the forces, it becomes more, difficult, right, to for you to actually, keep moving it up, because you are expending your energy to work against gravity to bring it down. So that is why this existence of this negative sign is here. Okay, so in some crude sense, this is how it works. Okay, so this is a scalar potential as a function of x, y, z, you can say. Obviously I am taking in this in real space, so you can also take it in one dimensional space, but I'm taking three dimensional space. There is a proof to this which I will be covering in other classes, but for now this is just a point. And you can easily prove this statement: curl of conservative force is always 0. So this is a direct consequence of the Stokes theorem. So you have the curl over a volume so it's expressed in terms of a closed line integral, and the work done in a closed loop is always 0. So that means curl of f is also 0. Okay, so these are the some properties. Okay, and coming to the more important properties in terms of celestial mechanics, right? I mean, not just celestial mechanics, but generally for central forces. So angular momentum is conserved. About the center of force. So, well, it is a kind of this thing, right? So you have a origin, and then you have a point P, and your torque, right, is going to be R cross F. So this is again, this comes from basic mechanics. Okay, so torque is just the the product of you have a body, right? It is pivoted about this point and it's rotating, right? And it is basically so you have a perpendicular force, and R is the distance between the line of action of the force and the axis of rotation. So if you take the axis of rotation as this, and this is the force F acting like this R is the distance between the origin, the axis, and the force. So that is what torque is, and torque is responsible for rotational motion. So technically you're saying that your in central forces though, right, in central forces your torque is going to be 0. Your torque is going to be 0 because if this is R, so R is technically radially outward. Your force is also outward, so there's only a radial component. So both your force and your r cap are in the same direction, so your torque is going to be equal to 0. So you can say your r is parallel to F, right? So yeah, and we know that torque is rate of change of angular momentum, so that becomes 0. So this proof, I see, I would say that this important point I'll be covering in mechanics also, but I just wanted to bring about some applications in this part of we studied about polar coordinates, so I thought this was just some extension, and that's what I thought I'll bring it apart. But I will be covering more about this in classical mechanics. But as of now, this is just a small snippet about central forces and direct application of polar coordinates. And yes, before ending this video, I would also, so I should have actually added this before, right? So in your acceleration term, right, only your, as a consequence of there being no torque and angular momentum being conserved, only your radial part exists, the transverse part goes away. So that is why another consequence is that your angular moment, your planetary motion will only remain in a plane. Okay, since angular momentum is conserved and there being no transverse component, it will remain in a plane. But in real life, yes, the plane does oscillate. You have to visualize the plane oscillating, but usually it is not a lot. It is very negligible, but as a motion, the plane is restricted in a plane. Okay, motion is restricted in a plane as a result of this, only a radial part existing and angular momentum being conserved. So you have to take a note of that. That's all for today. I will see you next time.